Okay, let's look at the first derivative test. It involves mainly looking for maxes and mins and then also identifying intervals where the function's increasing and decreasing. But I also wanted to point out some words that are used quite often in a section like this, and that's critical points. Critical points are where the derivative is equal to zero and when the derivative doesn't exist. And then the word extreme values is just another word for saying maxes and mins. And again, extreme values can occur when the derivative is equal to zero, the derivative doesn't exist, and endpoints. And again, these are really the only three spots where an extreme value can occur. They're not guarantees, meaning just because you have a derivative equaling to zero doesn't guarantee you're a max or a min. Again, I can look at the easiest function, y equals x cubed. That does have a derivative of 0 when x equals 0, right? Y prime of 0 would be 0, but that doesn't guarantee that that's a max or min. If you look at that graph just levels off. Okay, that's our nice cubic function. Comes down, levels off, and then goes down. But that is not a max or min, even though it does have a horizontal tangent at that point. Again, I could do the same thing for a derivative not existing. I could draw a piecewise function that did something like this, and then went off with a different slope. If you remember our differentiability lecture, it's not differentiable right there, the derivative doesn't exist, but that's not a max or a min. Now, most of the time, these do have, these are critical points, and these usually do lead to maxes and mins, but they're not guarantees. You must check to make sure they actually go from increasing and decreasing, and we'll talk about that in our video, but these are the only ways it can happen. If you've looked here and you've looked here, of course, endpoints, that's just taking the function and randomly just deciding, let's stop defining it there. So if we start here with some cubic function and we go like this, boom, and we just stop at that interval, well, of course, this is a minimum and this is a maximum. We've just sliced off the function arbitrarily. In this case, it was going up, and so this is a max. In this case, it's going up afterwards, so this is a min. Now, again, there are other two mins here. It looks like maybe a min right there and a min right there. And again, what we're going to do is we're going to look at the first derivative test to really find those. Most of this video really does just involve looking for where the derivative is equaling to 0. Okay, why are we looking for the derivatives equaling to 0? Remember, a derivative equaling to 0 means a horizontal tangent. A horizontal tangent line typically will correspond to a maximum or a minimum. Again, that's really what we're going to focus on in this video, and that's what the first derivative test does. Okay, so let's just start out with our first example, and I'm going to take you through, I think, 5 of them. Y equals 2x cubed plus 3x squared minus 12x plus 1. Okay, so let's find the maxes and mins, and let's find where the function's increasing and decreasing, and we're going to use a sign chart and the derivative to kind of take you through that, and then we can sketch what the function looks like without a calculator. Okay, so y prime, which means dy dx, right, the derivative. I'm going to use power rule here. So this is 6x squared plus 6x minus 12. I'm going to go ahead and factor that. Let's take out a 6x squared plus x minus 2. And I'm going to continue to factor x plus 2, x minus 1. Okay, that's my derivative. Well, when's the derivative equaling to 0? Well, the derivative is going to equal 0. Y prime equals 0 when x is going to be negative 2 and when x is equal to 1. Okay, I'm going to draw a sign chart here. Okay, and I'm going to plot my zeros. Put a little dot here for x equals negative 2 and a little dot here for 1. Okay, now again, I'm plugging in to the derivative, and I might as well plug it to a factored form. I'm going to see what the derivative is in this interval, in this interval, and this interval. I know the derivative 0 here and here. I'm interested in what it is between those. So I'm going to plug in a number bigger than 1. Let's plug in 4. And I don't really care what the number is. I just care whether it's positive or negative. So if you plugged in 4 here, it would make this term, 4 minus 1 would be positive. 4 plus 2 would be positive, and 6 is positive. A positive times a positive times a positive is positive. I'm going to put a plus sign there because the derivative is positive. Now, what does that say for the function? Well, if the slope, right, the derivative is positive, it means the function must be increasing. That's the definition of what a positive slope is, right? A positive rate of change. plug in a number like 0, 0 is between these two, it would make this negative, positive, still positive, and a negative times a positive is a negative. And then take a number like, I don't know, negative 10, it would make negative, negative, positive, and that's a positive. So what I've said here is that I'm saying that the derivative is positive, then it's 0 at negative 2, negative, 0 at 1, and then positive, which means my function is increasing, decreasing, and increasing. Let's just draw that. And again, I'm not even going to draw it on a grid. What I'm saying is my function is increasing, and then decreasing, and then increasing. And I would argue if you graph this cubic function, this is a positive cube, you'd expect to see that general shape. And what else do we know? Well, we know that the derivative is equal to 0 at negative 2 and 1, so we've identified those x values. Not only do we know that, but we know that at negative 2, this has to be a maximum. And this, at 1, has to be a minimum. Look, it was going up, and then it was going down. That's a max. This is going down, and then it starts to increase. That's a min. So we have identified both of those as maxes and mins, and then if you wanted to write out increasing and decreasing, which is kind of the same thing, our increasing intervals is going to be negative infinity to negative and 2, union with 1 to infinity. And then our decreasing interval, right, our function is decreasing from negative 2 to 1. And again, mainly this is what you're going to look at. We've identified maxes and mins, and we've identified intervals where it's increasing and decreasing, and we drew a pretty good sketch of the graph without using our graphing calculator. Okay, I'll do a similar one over here. So that was my first example. We'll do a harder one that's not just a polynomial. How about y equals 3 over x squared plus 1. And again, let's pretend we don't know what that graph looks like, and let's take a derivative. Okay, well, the derivative here, we got to do power rule, and maybe you want to think about this as 3 times x squared plus 1 to the negative first power. So take a derivative. I'm going to get negative 3 times x squared plus 1 to the negative second times the derivative of the inside. Okay, I'm going to rewrite that. Again, I had to use chain rule here, so that's negative 6x all over x squared plus 1 squared. And again, let's do a sign chart. I'm going to plot when the derivative is equal to 0. Now this one should be pretty easy to look at. When is this equal to 0? Well, if you set this equal to 0, no x value is going to make this make equal to 0, right? If you have one fraction equals 0, the only way that's equal to 0 is if the numerator is equal to 0. Well, when is 6x equal to 0? Only when x is equal to 0. So I know that the derivative is equal to 0 when x is equal to 0. Okay, I can plot that, and then I can plot points to the right. So let's plug in 5. Well, look, this is easy because this is squared, so it's always positive. If I put in a positive number like 4, I get negative 6 times 4, and I get a negative derivative. If I put in a negative x value, I get a positive derivative. And so what is 0? This says that the derivative is positive. That means the function is increasing and then decreasing, so this guy has to be a max. And if you look at the graph of this, it looks like this. It's kind of a nice hump right at 0 where 0 is a max, and look what happens. It's increasing from negative infinity to 0 and then decreasing from 0 to infinity. So again, the first derivative test is looking at the derivative before and afterwards and deciding max and mins, but it's also identifying all of these increasing and decreasing intervals for us. All right, let's look at another example. Let's look at y equals e to the x times x minus 4. That might be one that you're not really sure exactly what it looks like, but let's investigate using the derivative. So y prime is equal, I'm going to have to do product rule here, the first function times the derivative of the second plus the second function times the derivative of the first. Now remember, the derivative of e to the x is just e to the x. All right, I'm going to factor out an e to the x. 1 plus x minus 4. I can go ahead and drop those parentheses. I get e to the x, and this is just x minus 3. And again, we want to know when is this equal to 0. Remember, e to the x, well, that's never equal to 0. So what x value makes this thing 0? Only x equals to 3. So we know the derivative is equaling to 0 at 3. And then let's check values above 3 and below 3. So if I plug in values like 5, e to the 5, that's always just a positive number, and then 5 minus 3 is positive, a positive, and a positive make a positive. And if I plug in like 0, I get negative, and I get 1. I mean, really, I just get a positive, and I get a negative. So this must be some minimum. It's going to go down, and then it's going to go up. Again, if you looked at the graph of this, it would be something like, it's going to go like this, and then down and up. And what we did is, we identified that this minimum value has an x value of 3. 1, 2, 3. And again, if you wanted to find more y values, you could plug into the function. But again, the first derivative test has identified this as a minimum. It's identified it's increasing from 3 to infinity. It's decreasing from negative infinity to 3. Okay? What if I gave you, what if I just gave you the derivative? I never told you the function. What if I said y prime is equal to x times x minus 2 and x plus 4 squared? Well, we'd be interested in when the derivative is equaling to 0. Well, negative 4 is going to make it 0. 0 will make it 0. And 2 will make it 0. Okay, what's going to happen here? Well, let's check just values. Let's say x is 10. 14 squared is positive, positive, positive. 4 positives make a positive. What if we use 1? Positive, negative, positive, negative. What if we use negative 1? Negative, negative, positive, positive. What if we use negative 10? Negative, negative, still positive. Even though negative 10 makes this negative, we're squaring it. Negative, negative, positive. And do you see on this case, this is the first case, there's no sign change here. This is increasing. It's got a derivative of 0. Increasing, decreasing, increasing. So what happens here? Let's draw a graph. That means that this function is increasing, but then has a slope of 0, increases, decreases, and then increases. That's what this function would look like. So what we said is there is a horizontal tangent at negative 4. There's a horizontal tangent at 0. And there's a horizontal tangent at 2. But this is increasing and still increasing afterwards. This just levels off. Again, it's a derivative equaling 0 that does not lead to a max or a min. This ends up being increasing and then decreasing. Well, that's a maximum. This is decreasing and then increasing. And that's a minimum. Again, we've investigated this function by just looking at the zeros of the derivatives and finding intervals where it's increasing and decreasing. Again, we would say increases from negative infinity to negative 4. We have to skip negative 4, union with negative 4 to 0, union with 2 to infinity. And then we could say decreases from, I guess, just 0 to 2. And again, we're doing the first derivative test to find maxes and mins, but also in intervals where it's increasing and decreasing. And again, we're going to use the sign chart and investigate the properties of the derivative. We're seeing whether the derivative is positive or negative. Remember, we're always plugging these values into the derivative. We plug values above and below 3 into the derivative, not the actual function. I don't care if the y value is positive. I want to know that the derivative is positive, because a positive derivative means a positive rate of change, which means the function is increasing, meaning it's going up. A negative derivative means the function is going down. Again, this is all going down here. This isn't the best graph I've drawn. This should asymptotically approach y equals 0 here. Okay, let's do one more example, and then we'll be done with this. Okay, the last one we will look at is y equals x to the 2/3 times x minus 5. This has a decent amount of algebra in it. Okay, so there's a variety of ways we can approach this. We can treat this as product rule. It's kind of messy. We can multiply it in and then take a derivative. In the end, it doesn't matter. You're still going to have to solve it. Let's do product rule. Let's pretend you didn't want to multiply this in. So we have x to the 2/3 times the derivative of the second function, which is 1. plus the second function times the derivative of x to the 2/3, which is 2/3 x to the negative 1/3. Okay, let's simplify this if we can at all. Let's make it look a little better. This is x to the 2/3, and this is what? 2 times x minus 5. The 2 and the x minus 5 are in the numerator. This 3 is here, and this is x to the 1/3 in the denominator. Again, and what we want to do is we want to set, well, remember, we're always looking for when is y prime equaling to 0. So we're going to set this guy, x to the 2/3 plus 2 times x minus 5. We're going to set this equal to 0, and we're going to find the x. Okay, so setting this equal to 0, I'm going to add this to the other side, or subtract this to the other side of the equation and get negative 2/3 equals to x minus 5, 3 to the 1/3. I'm going to multiply by this over here and get negative 3. X to the 2/3 times x to the 1/3 is just x. 2 times x minus 5. I'm going to go ahead and distribute that. And then I'm going to add the 10 over to here, add the 3x, and I get, nice, easy, x equals to 2. So x equals to 2 is an x value that makes the derivative not exist. Okay? Everyone kind of see this so far? Okay, now don't forget, not only is this where the derivative is equal to 0, but is there a spot where the derivative doesn't exist? This is where the derivative is equal to 0. Is there a spot and you're like, oh man, check that out. If I let x equal 0, the derivative doesn't exist at 0. So I have to include x equals 0 as a possibility. Both of those are on my number line. Again, none of the other examples really had that because they were just too easy. This one has a derivative not existing and a derivative equal to 0. And now we have to check. Okay? And when you plug these in, this is going to be a little more difficult to plug in and actually see whether it's positive or negative. But here's what you're going to get. If you plug in a negative number, you are going to get a positive derivative. If you go from 0 to 2, you're going to get a negative. And if you plug in a big number like, 100, of course you're going to get a positive. There is going to be a sign change on each of those things. And again, maybe you just want to take x equals to 1. X equals to 1 gives you a 1 here. It's going to be 1 minus 5, which is a negative. A negative times a positive is a negative. A negative divided by a positive, again, is going to be a negative, and that's going to be bigger than 1, which will make this negative. And you can go through that. But for the sake of the video, why don't you just believe me that when you plug in values here, here, and here, again, I'm plugging into the derivative, not the function, the derivative, and I'm showing you that the derivative is positive, and then negative, and then positive. So what is 0? Well, if the derivative is positive and the negative, that means the function is increasing and then decreasing. That's a max. And then that's a minimum. You can confirm this because if you graph this guy, it's going to look something like, and then it's going to go, and so if you look here, this is some crazy where the derivative doesn't exist at 0, and then this is some minimum where the derivative is equal to 0, right? This is your horizontal tangent, which we found here, and this is where the derivative doesn't exist, which we got here, and again, because we looked at the domain of the derivative. And again, I know that the function has to look like this, even though I have no idea really what that looks like. This is a pretty complicated function that you don't come across very much. But again, looking at the first derivative test, looking at the derivative before and after a 0, or before or after a derivative doesn't exist, I've established that this is a maximum and this is a minimum. The interval of increases, right? This is going to increase on the interval negative infinity to 0, union with 2 to infinity, and it's going to decrease from 0 to 2. And I know that this is a max and this is a min by that analysis. So I've given you, I think, 5 examples of, I started out with some polynomials and I threw in an exponential and I threw in one where you just knew the derivative. But hopefully this is a good review of the first derivative test, showing you maxes and mins, showing you increasing and decreasing, showing you critical points, and showing you even where a critical point on the previous example didn't mean that it was a max or a min. Again, those are spots you need to check, but they're not always maxes and mins.